Welcome. This is Tanmay Gupta presenting our work on contrastive learning for weakly supervised phrase grounding. Our goal is phrase grounding, which is the problem of mapping noun phrases and captions to regions in the image. Usually, learning this requires access to ground truth mappings between phrases and regions. But can we learn this mapping without explicit grounding annotations? Specifically, we are interested in learning phrase grounding from captioned images without having region word correspondences during training. We believe this to be possible given basic representations of images in language, such as that provided by pre-trained object detectors and language models. We are also interested in how a language model can be used to learn phrase grounding. We know that language models, such as BERT, are powerful feature extractors. We show that their generative capability also lends itself to learning grounding. A common approach to weakly supervised grounding problem is multiple instance learning. Images are treated as a bag of regions. A bag is labeled positive for all words mentioned in the caption and as a negative for remaining words in the vocabulary. For example, for the word skateboarder, the image on the left is a positive bag, while the image on the right is a negative. Each region predicts a score for all vocabulary words, and scores are aggregated across all regions to get predictions for the bag. Common methods of aggregation include max or average pooling, noisy OR, and attention. Once these bag level scores are computed, the problem can be treated as a supervised image classification problem with region level scores as latent variables. Align to ground is a recent approach that could be viewed as multiple instance learning with attention-based aggregation while treating the entire caption as an image level label. The region phrase correspondence is learned as an intermediate step while learning to match images to captions using a triplet loss. Our approach is similar in the use of attention as an intermediate computation step to assign regions to words, but we offer a novel perspective on weakly supervised grounding as optimizing a lower bound on mutual information. A grounding model consists of a pre-trained object detector to extract region proposals and image features, a language model to compute contextualized word representations, and a learnable attention mechanism to assign regions to words. For learning, our key observation is that estimating mutual information between a set of regions and caption words requires computing their alignment. Therefore, by maximizing a lower bound on mutual information, we expect the attention to learn grounding. Contrastive training using InfoNCE involves learning a compatibility function between the variables we wish to compute mutual information for. We want to learn a compatibility function between a set of region features R and contextualized word representations W. InfoNCE objective encourages higher compatibility scores for true region word pairs than incorrect pairs. Images with corresponding captions serve as positives, and negative pairs could be constructed by pairing the original caption with a randomly sampled image, or by pairing the original image with a randomly sampled caption. We designed the compatibility function such that achieving a higher compatibility score corresponds to correctly assigning regions to words. For negative pairs, we expect the words to not select any region strongly and therefore produce near uniform attention over regions. Instead of randomly sampling negative captions from the dataset, we create effective negatives for contrastive learning through word substitutions. For example, the word donut in the true caption is replaced by cookie to create a negative caption. We will take a closer look at this in a moment, but first let us look at the compatibility function. Say we are interested in computing compatibility between the set of regions and the word mug in context. We begin by extracting region features and contextualized word representations. Keys and values are extracted from regions using feed-forward networks, while query and value features are computed from contextualized word representations. To compute attention for mug, we take an inner product of its query representation with region keys and expect a high attention score for the second region which contains a mug and low scores for other regions. An intended visual representation for mug is constructed using a weighted average of region values using attention scores as weights. Finally, the compatibility score is computed as an inner product of the value representation for mug and the attended visual representation. Once trained, the attention is used as region word assignment scores for grounding. A natural question is, does the phrase grounding performance improve as we maximize the InfoNCE bound? The answer is yes, but only up to a certain point. Here, as models with different choices of query key value networks are trained on the COCO train set, we visualize their info and CE bound on the COCO val set on the x-axis and grounding performance on the Flickr30K val set on the y-axis. For each model, the dots correspond to measurements and their moving average is denoted by a dashed line. We observe that for all models with more training iterations, grounding performance increases with increasing value of info and CE bound until it reaches peak performance denoted by a star. While training further continues to push the info and CE bound, grounding performance starts decreasing. While training does not require grounding annotations, this result highlights the need for a val set with grounding annotations for model selection. Note that nonlinear query key value networks not only achieve better peak performance, but do so with fewer training iterations. In addition to a novel objective for weakly supervised phrase grounding, we also propose an approach for constructing hard negative captions for contrastive learning. Given a positive caption, we use a pre-trained language model to generate contextually plausible negative word substitutes. We denote the word to be substituted by S and refer to the remaining sentence as context denoted by C. First, we feed the context with a mask token into a language model such as BERT to generate a list of candidate substitutes by selecting high probability words. However, this would contain words like minivan and vehicle, which are likely to be true for the image and hence not suitable for use as negatives. To identify such near synonyms and hypernyms, we again produce likelihood scores for the selected candidates, but this time conditioning on the true word instead of using a mask token. We now expect higher scores for words with a similar meaning as the original word than semantically distant words. To select words that are contextually plausible but are not near synonyms and hypernyms, we re-rank the candidates based on the ratio of these two distributions and discard the words with the lowest scores. We perform an ablation study to understand the gains from using language models as feature extractors and for negative caption construction. We begin by looking at models trained without negative captions. We observe a roughly 10-point gain from using pre-trained BERT features as opposed to using outputs of a randomly initialized BERT as language representations. Randomly sampling negative captions from the dataset yields roughly the same performance as not using negative captions. However, using contextually plausible negatives yields an 8-point gain in performance, and rejecting near synonyms and hypernyms using re-ranking yields another 2-point gain. Overall, using the language model to construct negatives yields a significant gain in addition to their contribution as feature extractors. Our model, pre-trained on COCO without grounding supervision, establishes the new state-of-the-art on the Flickr30K Entities benchmark. While we do improve upon existing methods by a large margin, we note that a completely fair comparison is difficult since all existing methods use different visual features. We use the same visual features as align to ground, but use BERT for language representation due to its prevalence in the vision language community, while align to ground uses a GRU-based encoder. For code, qualitative results, and more, please visit our project page, and thank you for your attention.